kappa is much, much less than the index of refraction. The only way kappa can be small is if the conductivity is small. So remember that then the index of refraction in that particular case with kappa much, much less than n is just equal to the square root of epsilon mu, where epsilon's the real part, mu is real. And kappa, oh, I did write that down, is going to be approximately equal to, because remember we're taking the square root, maybe I'll write it out here, of that whole thing there, which is n plus I kappa, right? So I'm taking the square root of this complex quantity here. But if sigma is small, or omega is very large, then this term will be very small compared to that term, and so that means that I just do a Taylor expansion, okay, for this term being small. So the whole thing in that particular case is square root of epsilon times 1 plus I times 2I sigma over omega epsilon. I hope I did that right. 1/2 for the square root. All right, so I just took this thing and Taylor extended it for small conductivity. Right? So that means that kappa is equal to 2 pi sigma over omega epsilon, which I have written here, and someone can check to make sure whether this is correct, as equal to 2 pi sigma over c times the square root of mu over epsilon. Speed of light. So yeah, works. Okay? Well, we know what kappa is then for a poor conductor. Now, what orders of magnitude are we talking about here? Typically, we can treat things this way when, let's say for a semiconductor, n, that's the index of refraction of silicon, for example, is about 3.5 in the optical range, 3.5, 4. And kappa is of order 0.001. So that's a pretty good approximation. So then in that case, now I can, remember we know what K is. K is just omega over C n plus I omega over C kappa. So then I can write out my propagating wave as I've got over there. And the electric field is E0. Oh, let me just arbitrarily choose to put my electric field in. My propagation direction is C, and my electric field points in X. Okay? So this is a specific case, not, it's an example. So the electric field will look like that. Ex, e to the minus I omega t minus omega over c square root of epsilon mu z e to the minus omega over c kappa 2 pi sigma over c the square root of mu over epsilon z. This is the decaying part. This is the oscillating part. So this is just a traveling wave, which travels, has a wavelength that is altered by the factor of the square root of epsilon mu. So that's a slowly decaying wave. We get a little bit of a complication when we consider the magnetic field in this case. But we can pretty much ignore it for the poor conductor, because the magnetic field is the index of refraction times E naught y hat e to the minus I omega t minus omega over c. And I'll just cheat here and write complex index over refraction. I'm not splitting it out. It's the same, all right? The e to the I terms are the same, but there's an index over there. This is the square root of u epsilon there, right? There's an index of refraction term there that is complex. And what that means is that the electric field and the magnetic field are now out of phase with one another. For propagation in vacuum, the electric and magnetic fields are just doing this, right? When it's propagating through a material that's got a conductivity, the two are slightly, that's very out of phase. But they're slightly out of phase with one another, right? Now the complication there is that then at any instant, E cross B might not be exactly what you think it might be. I'll just give you that warning. So the Poynting vector gets a little bit more complicated as well. But as long as the conductivity is low or kappa is small compared to the index of refraction, you're good to go. Right? You can ignore everything else. How about for a good but not great? Conductor. All right. Then I'll write things. The solution looks like this. It looks pretty much the same. E0 x hat. I'm going to rewrite things a little bit. I'll write this e to the minus alpha z, and I'll define alpha, right, times e to the minus, and I'll redefine beta, minus I beta z minus I omega t. Traveling wave, decaying wave. Right? I still got a traveling wave and a decaying wave. And in this expression, alpha is omega over c kappa. And yeah, I'll leave it. Beta is the real part times omega over c as well. Now the magnetic field, we have to really be clear about the fact that there's a complex portion in there. So I'm going to write, but this is really the same as what I've got there. C over omega alpha plus I beta. So explicitly, I've written the, yeah.
Is that e to the minus I beta z minus I omega t?
Yes.
Okay. The I is kind of hard
So
to
this
see.
is the traveling wave portion here. The I is not too clear on the line there, I'm sorry. Z cross E. Because once again, I'm using example where K, the propagation direction is Z, and the electric field direction is X. And it's an oscillating wave.
And you switch to negative?
Whoops.
Negative I, and you switch to negative I from positive I?
That's a phase change of pi. What is a phase change of pi among friends? Okay. So there's my electric field, there's my magnetic field. All right. I can rewrite this as C over omega. Absolute value of K being the 2 pi over lambda, right? A wave vector. E to the I, new thing, phi, Z cross E. I'm explicitly going after the fact that the magnetic field is out of phase with the electric field. And I've got my two components here, my conductive loss, and my, actually I shouldn't call it loss. Yes, I can. Conductive loss and my real part of the index of refraction, which just changes the wavelength and the speed of propagation. And in this expression, I apologize to people in the back, K is equal to alpha squared plus beta squared. And it can get messy. And phi is equal to the arctangent of alpha over beta, but 4 pi sigma over omega epsilon. I should have written this, I will write this out in terms of conductivity and dielectric functions and frequency. This K is equal to square root of mu epsilon omega over C 1 plus 4 pi sigma over omega epsilon. I have posted these already. 4 pi sigma over omega epsilon squared added to 1 to the 1/4 power. But this is just a matter of, you know, I've got this thing here and I need an amplitude. Then I take my epsilon and my alpha and beta, translate it into conductivity, frequency, and conductivity, frequency. There's got to be something else that I need to include in there. Oh, dielectric function. Put that all together, and I end up with a definition for the amplitude of the wave function, which is, of the wave vector, which is omega over c. That's what it would have been. Then if I were transmitting through a material with no loss, with no conductivity, I would have a square root of mu epsilon there. So this is what it would be in a dielectric. And then this term gets added because now I've got conduction losses. So explicitly, the magnetic field and the electric field, they are definitely out of phase with one another, and we have to take care with our cross products then, as you have actually learned with the homework that you did, where you were calculating the spin of a wave. The very fact that you had one component delayed with respect to another component suddenly made the cross product appear, whereas before there was no cross product. If you had linear polarization, you do the cross product of E cross A, and there is no cross product. But if you have a circular polarization or elliptical polarization, a phase difference, the cross product exists. Same thing here. Well, not the same thing, but you've got to worry about similar ideas. All right, then finally, good conductors. Very good conductors. Great conductors. To be consistent. All right, then the next question is, well, what are we going to do? Yes, that's right, Seiji Ozawa.
What's the qualification for good but not great?
Good but not great means I have to pay attention to both. That's a good question. Let me say here that kappa is less than n, but not much, much less than n. So this is poor, much, much less than n. Over here, less than n, meaning that it might be a tenth of the index of refraction, or just 100th of the index of refraction. And over here, what we're going to do is we're going to say that, yeah, let's look over here. I'm going to say that 4 pi sigma over omega, that's the conductivity divided by the frequency, is, in this case, much, much greater than epsilon. So kappa is greater than the index of refraction in this case. Okay? So that was what qualifies great. And in that case then, complex index of refraction, just taking that, is approximately the square root of 4 pi sigma over omega mu. I seem to have lost a mu in here. Yeah.
I think you've made it 1.
This is mu times epsilon, and that's mu. But mu is usually 1. I just want, I got a mu over there, I should have it in here. All right, which, this is an easy square root to take, because it's just the square root of I times the square root of the real part of what's going on here. And the square root of I is 1 plus I divided by the square root of 2. What this is telling us now is that the real term here and the imaginary term are the same magnitude, not same magnitude, they are equal to one another. So in the time that it takes the wave to oscillate, it decays. Before it can oscillate once, it has decayed. Right? It's an overdamped wave, in fact. Strongly damped, but actually overdamped. So the electric field looks like this. E to the minus I omega t minus z over. I'm going to introduce a new term here because that's what we do, just to mess with you.
X hat.
Now, I'm going to introduce a term. Yes, thank you. Delta. Why? Because that's what the texts use when you get to if you get into an electromagnetics text that's dealing with metals, they use the term delta, and I'll give you the words to go along with that. Okay. E to the minus z over delta. Right? So this thing here, delta, is called the skin depth. And it's the penetration depth for the light. That doesn't mean it's absorbed in that depth. What it means is that it's trying to get in and it gets reflected, actually. A perfect metal doesn't absorb anything. It just reflects the wave. And that skin depth is equal to the speed of light divided by the square root of 2 pi sigma mu omega. The interesting thing about this is that remember that the magnetic field, right, is equal to that complex index of refraction times E naught times some other terms, y hat, other stuff. Right? The other stuff is the oscillating and decaying portion. So this is the same here as there. But here, I've got this complex index of refraction. The imaginary part, because sigma is big, 4 pi sigma over omega is large, that term can be very big. It's much bigger than the normal dielectric constant. It could be 100. Which tells me that for the wave that's propagating in a conductor, it's the magnetic field that's carrying all of the energy. The magnetic field is much larger than the electric field in a very good conductor. It's the current, Basically, you have this wave that's incident, and the wave that's incident kills the electric field and ends up causing current to slosh back and forth, because there still is a tiny electric field. And that current gives rise to the magnetic field. And the magnetic field doesn't experience loss the way that the electric field experiences loss.
the stuff in the parentheses for that B, that's the two E terms, right?
That's that. Okay, so the wave decays in the skin depth. And by the way, there's another thing that this tells us. I'll just mention the orders of magnitude. In the microwave regime, 10 to the 9th hertz, the skin depth for copper is about 1 micron. So that means that if I had a chunk of copper and I tried to send an oscillating electric field down, current through the copper, what's going to happen is that all the current's going to end up being carried at the surface of the copper. There won't be any current on the inside, right? Basically, the copper itself will exclude propagation at those high frequencies. So in a coaxial conductor where you're sending lots of, you're trying to send power down the conductor, what's happening is that the power or the current is being entirely carried in this 1 micron thin region at the surface of the copper core. So there's no point in putting big, thick copper wires when you're carrying RF signals. Yes?
How pure do you have to have metals to have skin depth and be great conductors?
Almost every metal that we know by this measure is a great conductor.
Even alloys?
Even alloys. Brass is a great conductor by this measure. Yeah, right.
If you take a really thin sheet of conductor, can you just send an electromagnetic wave?
As long as the conductor is thinner than the skin depth, it goes right through. Which is really important for
Tunneling.
stealth technology.
And
Okay.
tunneling.
What's the classical version of tunnel?